explain a few things about the failure modes in composites. Just like in metal, composites has different modes of failure. In metal we recognize elastic deformation and plastic deformation and ultimately rupture of the metal pipe or whatever structure it might be. For composites that's a little bit different. In composites we recognize fiber failure or rupture. We have interlaminar shear, cracks due to interlaminar shear, and we've got microcracking. And microcracking is the mode that we will be focusing on today. Basically it is the formation of tiny microcracks, the word already says it, in a laminate as a result of deformation. And I'll try to explain how that works. The reason that I'm focusing on microcracking is that that is the primary failure mechanism that we see when we're loading composite pipes under a burst rating, for instance. That's the first thing that will happen is microcracking. For a lot of composite materials it is not a big problem to have microcracks in them because it doesn't affect the performance. But for a pipe, which is a fluid holding body, it is a big problem because a microcrack will cause a leak. And of course a leak in a pipe is a failure. Now what happens? You have to imagine that a composite is a combination of resin and fibers. And I'll try and visualize that by having a piece of material, and inside that piece of material we have fibers. And you can imagine if I load this piece of material in the direction of the fiber, the actual load will be taken on by the fiber. And in this situation we don't have a big problem because the resin that is in between the fiber hardly takes any load. All the load will be distributed through the fiber from one end to the other end of the piece of material. So when we do a test like this and we have a load in the direction of the fiber, we will not see microcracks. The failure mode will most likely be rupture, fiber failure. But in real life we don't have material like this. A pipe is always a shape that has a bidirectional loading. So there is not just a load, say, in the longitudinal direction, but if you have a pipe, there is also a load in the circumferential direction. So there's a bidirectional load. This means that we also need fibers in the other direction. So we have fibers in the other direction as well. And basically we have alternating layers of fibers in the one direction and fibers in the other direction. As layer to layer they differ. But because we have fibers in the other direction, it means that we can also load the pipe in two directions. And this is basically where the microcracking problem starts. Because these fibers, the vertical fibers, they don't work in the horizontal load and the other way around. The horizontal fibers, they don't work in the vertical load. Actually, they're basically just hampering the performance of the material. And that is caused by deformation. Deformation due to the hydrostatic pressure, for instance, means that the pipe will stretch, will elongate, and the pipe will elongate, and therefore the material has to accommodate for that. Now, when I'm pulling on the fibers, that is no problem. But if I'm pulling in the horizontal direction, the layer with the fibers in the vertical direction also have to deform the same way. So what does that look like? I'll focus on the vertical fibers and the horizontal load. So the wrong load for the fiber direction. I'll draw them out here. What happens here? The deformation of this piece is determined by the stiffness of the horizontal fibers, so the fibers that are in the correct direction. That deformation is not high because the fibers take a load, but it is still there. And contrary to what you might think is that glass fiber is very flexible. A glass fiber composite is even 10 times more flexible than steel. That means for any given load that the deformation is also 10 times more than you would expect for a steel pipe. And that gives the following effect. That means that the fibers that are in the wrong direction, so in the layer that has the vertical fibers, they will be moving outward. They will be stretching in this direction, in the horizontal direction. But there's nothing to keep them together inside this layer, except for a little bit of resin in between the fibers. So basically, the material's elongating, and there's only the resin keeping the fibers together. The fiber itself is not strengthening it in the proper direction in this given layer. Now, the resin has some strength, but what is actually determining the fracture of this piece of material is the strength between the fiber and the resin, the interface between the fiber and the resin. Now, glass fiber is in principle inert. It doesn't react with anything. And in composite technology, we use something that is called a sizing, which is a coating, a silane coating on the glass fiber to make it adhere to a resin anyway. But still, that is a compromise. The adhesion is never perfect, and it is the limiting factor for the strength in this direction. Because in the other direction, we had fibers taking the load. In this direction, we don't have fibers. We just have this resin to glass interface. Now that means that the deformation that is caused by the load and by the flexibility of the horizontal fibers determines the deformation of this layer as well. This layer simply has to go along with the other one. And that means that not the load or the stress in this layer determines when it's microcracked, but the deformation causes the moment when it microcracks. And the deformation is caused by the modulus and the stress in the fibers horizontally. So there you have it, actually. This is the cause of it, and what we can do to make this, to mitigate this a little bit, is to get resin that is a little bit more flexible. So if the resin is more flexible, we can allow for more deformation in this direction without failure. But that's only very limited, because if I look at this layer from this view, and I look at the fibers, actually the fibers look like this. This is roughly the stacking of the fibers. So you can already see that there's a lot of glass fiber and very little resin, because in between here is the resin. See? Now, the diameter of a fiber on average is 10 microns. So you can already see that the thickness of resin is probably 2 microns or something like that. This means that if we want deformation in the same direction, so I'm putting on the same load again, we're asking this layer to deform, and we're depending on the resin to allow for that deformation. But there's only very little resin to do that. So the flexibility of this layer is a combination of the flexibility of the glass and the flexibility of the resin. So even if I were to make the epoxy resin a lot more flexible to allow more deformation and therefore to allow more load, I'm only using maybe 20% in the total bulk of the material of that flexibility. So if I increase the flexibility of my resin from 2 to 6%, in practice that would mean an increase of the flexibility of the entire layer of 0.1 to 0.2% or 0.15 or something. It's very little, because most of the makeup of the layer is glass fiber, and that is high modulus. Another disadvantage of getting more flexible resin is that the temperature resistance decreases with it. So there's only very limited effect of what we can do with toughening resins, because inside a laminate it doesn't do much. The driving factor for the stress level that creates microcracking is the E modulus of the horizontal fiber. This. And that's why carbon fiber is such an effective material. The E modulus of carbon fiber is, from the top of my head, 7 or 10 times higher than the E modulus of glass fiber, depending a bit on the grade of carbon. And that means that for the same stress, the elongation or the deformation of this horizontal load is 7 to 10 times less. And that effectively means that the stress level where microcracking occurs in this layer is also 7 times higher. And that's why carbon fiber is so effective in a composite material. Unfortunately, carbon fiber is 20 euros per kilo and glass fiber is €1.50 per kilo. So this is a big compromise that we're making. Nonetheless, for exceptional programs, for projects that really have a specific need, we could always consider using carbon fiber, which will obviously push the boundaries of microcracking. Thank you.